thank you very much. Thank you to the organisers for letting me speak. Okay, yeah, so quick overview. You can't really talk about contact geometry without talking about symplectic geometry, and this holds true in infinite dimensions as well. So basically the main theorem is that actually, yes, you can do contact geometry in infinite dimensions, and though actually this does produce physically useful and physically sensible results. Yeah, okay, so for this talk we restrict ourselves to Banach vector spaces and smooth maps between them, but a lot of the results hold for more general spaces, locally convex vector spaces in particular, as well as manifolds modelled on all of these spaces. Yeah, and then basically this is quite a good book for all things infinite dimensional, for all things to do with geometry and infinite dimensions. And basically, if you take away anything, I think it's worth taking away that actually geometry in infinite dimensions is not that much scarier than just normal geometry. And in fact, sometimes it's easier because you don't have to use coordinates, because you can't use coordinates because that'd be kind of ridiculous. So anyway, our first definition is that of a weakly symplectic vector space. So in infinite dimensions, you can't restrict yourselves to cases where your vector space is dual to, or is isomorphic to its dual, because there are so many infinite dimensional vector spaces where this just isn't true. And so we'd be restricting ourselves to only really boring cases. So we have to consider weakly symplectic forms. And so we call the bilinear form omega weakly symplectic if this contraction map here is injective. And obviously in finite dimensions, injectivity and bijectivity would be equivalent, but in infinite dimensions this doesn't hold true anymore. And then, okay, so if we do have an isomorphism, and if omega sort of, creates this isomorphism, then we call it a strongly symplectic vector space, because it's stronger. Okay, and then, so in infinite dimensions, a K-form is just it's a map which is smooth in one argument, and continuous, linear, and alternating in all of the other arguments. Or you can think of it as a map from a manifold to the kth wedge of the duals. And you can refer to Kriegler and Call for that. And importantly, so as long as you do everything carefully, and as long as you restrict yourselves to a nice enough subclass of locally convex vector spaces, then lots of the expressions that we use in finite dimensions still make sense in infinite dimensions. So we can take exterior derivatives, interior products, B derivatives, etc., etc. And so, in particular, in infinite dimensions, we have symplectic manifolds where we take a 2 form, which is closed, and as long as every tangent space is still a weakly or strongly symplectic vector space, then we call it a weakly or strongly symplectic manifold. I guess don't worry too much about what a tangent bundle is. It's sort of just for every point we are going to associate with this, a copy of the vector space, which I guess sounds obvious. Oh yeah, and then so what's the point of this? Oh yeah, so then equivalently, this map flat, which is our contraction map, is injective or bijective. And then obviously this is, this covers a lot of bases. But so in infinite dimensional symplectic geometry, Hamiltonian mechanics arises from fixing your Hamiltonian vector field to satisfy this. The main difference being that in infinite dimensions, because we only assume injectivity and not bijectivity, then not every function has a Hamiltonian vector field. Okay, so here's an example of a infinite dimensional symplectic form. So if we take V to be a Banach space and V prime to be the space of bounded and linear maps, and if we consider this to be omega, so we're pairing the vectors and the covectors, but we're sort of swapping them around, and so this gets us a non-degenerate bilinear form that is in particular anti-symmetric. And so if we just make this parallel on our vector space v by v prime, then we get a two form. Any questions? Okay, cool. And then so this is in particular a Fraser example. Although, so interestingly, I used this as an example in my paper recently, but I think I restricted it to a case where it actually is no longer Fraser and is actually Banach. So, you know, sometimes these things can go wrong. And so basically this is, in particular, a weak symplectic form because of the existence of the Hodge dual, which would take a little bit longer to explain. But so this is a nice example, I think. And also, interestingly, this sort of makes the Hodge star into like a Kähler, sort of into an almost complex structure that sort of then makes everything Kähler. I guess maybe we'll find out more about that tomorrow. Okay, so for this part of the talk, we go back to finite dimensional geometry while I explain contact geometry. Okay, so a strict co-orientable contact manifold is a pair M eta consisting of a odd dimension manifold M and a one form such that eta wedge d eta to the n is a volume form. Yeah, and then this gives us two distributions, a horizontal distribution and a vertical distribution. So the horizontal distribution obviously arising from the kernel of eta, and the vertical distribution arising from the kernel of d eta. Yes, okay. And then, so it turns out actually this line, last time I gave this presentation, I was correct on this. It's a slightly subtle point. Maximally non-integrable and this condition are slightly different things. But we'll get to that later actually. Okay, so the point being that, so that's not the only condition that's not the only condition that implies that a form is contact. So this is the definition, eta wedge d eta to the n being a volume form, but then equivalently, if the tangent bundle splits into our horizontal and vertical bundles, then it's contact, if and only if, and also it's contact if and only if d eta is non-degenerate when restricted to h.
Did you ask anything about the ranks of H and V?
Oh, I should have mentioned, yeah, so H automatically has co-rank 1, because it's the kernel of a map into R.
And so you need Tn to split to something of rank 2n and something of co-rank 1, right?
Yeah, exactly, yeah. And so that's actually sort of what makes the manifold necessarily odd dimensional, at least in the finite case.
Yeah, and this V needs to be maximally non-integral,
Yeah. Oh, H needs to be maximally.
No,
Yeah.
or H,
yeah, okay, so then that means that we have a sub-bundle, which is a symplectic bundle. And in particular, importantly rather, we have this map flat, which is, so part of it is this contraction map that we had before, but then we also have this eta x times eta blank that we add on. And we want this to be, in finite dimensions, an isomorphism of C infinity M modules. And so these four conditions here are all equivalent to each other and all equivalent to a form being contact. Yeah, so it follows from rank nullity that V has rank 1, so it's a line field. And so we can pick a unique section which satisfies eta of R equals 1 and d eta of R equals 0, and this we call the root field. Yes. Okay. And then, so we can do contact Hamiltonian mechanics. So, yeah, basically, we pick so if any function h, in finite dimensions at least, there is a unique vector field that satisfies these two conditions, and this is a slightly more succinct way of writing those conditions. And so as a quick example, that I'll blitz through. So if we take the harmonic oscillator, half q squared plus a half p squared, but then we add this kappa z, then what happens is when we put this through this equation here, what we get is these three equations here, and in particular this equation describes adapt harmonic oscillator. So instead of a harmonic oscillator that never loses energy, we've got a harmonic oscillator but that loses energy exponentially. So this is like the simplest, interesting example of a contact Hamiltonian system. Okay, now we get to talk about infinite dimensional contact geometry. So the point is that because contact geometry is useful for describing situations with dissipation or diffusion, we would like to be able to describe infinite dimensional systems that have dissipation or diffusion. For example, if I pluck a guitar string, then the guitar string loses energy in the form of heat or sound. And so we'd like to be able to model that. We'd also like to, maybe someday, not quite yet, model, say, non-ideal fluids, the Stokes equations. Lots of things like that. But then, so in order to do that, we obviously have to lose this definition of a contact form because it stops making any sense. We can't take the wedge product of infinitely many one forms because this stops making sense very quickly. However, H, the horizontal bundle, is a more fundamental object than eta. So often, actually, what you define first is H and then eta, rather than the other way around. And for dynamics, actually, you never use this volume form to do calculations. You use the map flat. And also, for the dynamics, we want the Reed field, and the Reed field is guaranteed to exist as long as we have the splitting of the tangent bundle. So, can we still define contact geometry in infinite dimensions? Yes, we can. I'm working on this bit. It has been submitted somewhere. Okay, so basically the theorem is that we can do away with the definition, and we can take the next three things and use these instead. So basically the following are equivalent for eta of one form on some infinite dimensional manifold, and d eta we actually have to assume it to be degenerate this time, because, well, I'll mention that in a second. So the following are equivalent. Our tangent bundle splits. We have a weakly symplectic distribution, and we have this map flat defined in exactly the same way, but instead we only assume it to be an injective homomorphism, because if we assumed it to be a isomorphism, then this would be assuming that our that it was isomorphic to its dual, which would be too strong, like in the symplectic case. And the proof is, I think, quite fun, and I don't think it's too difficult to come up with by yourself, and it would take me too long to explain for now. Yeah. What was I going to say about the dimensional constraints? I can't remember now. Maybe it'll come back to me. Okay. So this is just the main theorem repeated. And then, so here's an example. If we take a Banach space with dual E prime, and then we take R times E prime to be our manifold, and then so we take some Z in R, X in E, phi in E prime, then the following is a contact form. So I'm using hats and tills to represent like the first vector and second vector respectively, just to tell them apart. Yeah, and then so this is what our d eta looks like. And actually, if I'd been a bit more careful with the notation, this would look more similar to the previous symplectic example that I mentioned. But never mind. And so our vertical bundle actually is just sort of the line bundle represented by Z, and our Reed field is just 1, 0, 0 at every point. And our horizontal bundle is given by this expression here. Yes, okay. And then so we have a special case of the previous example as well. So if in particular E is an LP space, for some measure space, then E prime is an LQ space with P plus Q equals to PQ. And then we can write down this expression for the contact form, which is just this, but written in a slightly nicer way. So in particular, by the Darboux theorem, has anyone mentioned the Darboux theorem for contact forms yet today? Okay, well, by the W theorem, every contact form locally looks something like this. But then hopefully you can sort of see that actually this expression and this expression look fairly similar to each other. So this is just sort of like a LP space version of this expression. Okay, and then so here's some interesting properties of contact forms in infinite dimensions. So if our horizontal bundle is actually a strongly symplectic, subbundle, then our flat map is actually an isomorphism now. We can recover finite dimensional contact geometry using our definition, because if we assume that M is finite, then we find that M has to be odd, and we reproduce the fact that our that eta wedge d eta to the n is a volume form. And then we've got something that's almost the definition, but not quite. So if M eta is an infinite dimensional contact form, then for all k, eta wedge d eta to the k is nowhere zero. So this is almost our volume form condition, but not quite. It's like a sort of infinite chain of this volume form condition. However, the converse doesn't hold, because we can take a infinite dimensional contact form and some other manifold n paired with the zero form, and then so the product manifold would satisfy this condition, but it would not itself be a contact manifold. And so instead what we get is like actually a sort of Pfaffian form, or a Pfaffian problem, which is something that I've been meaning to look more into. Yes, okay. How am I doing for time? Not great. Okay, so we can form contact manifolds in much the same way as we do in finite dimensions, just by taking products with R by S1. And we also have a construction called symplectization, where we take a contact manifold and we make it sort of one dimension bigger, and we get a symplectic manifold by this construction. And then we can also do the opposite. So if we take a sufficiently nice submanifold, codimension 1 submanifold of our infinitely dimensional contact manifold, then we can actually, given these assumptions here about the existence of Loughborough vector fields and the existence of Hamiltonian vector fields, then we can actually produce a contact manifold with this construction. And actually, this construction and this construction are sort of adjoint to each other. So if we perform a symplectization, then we could actually get our original manifold back as a level set of contact type. Yes, okay. I'm going to have to blitz through the rest of these. Okay, so we define contact morphisms as morphisms which preserve the horizontal bundle. So in particular, they actually don't preserve the contact form, but they can formally preserve it. And so we call a vector field contact if the diffeomorphisms produced by the flow of the vector field are all contact morphisms. And so every contact vector field has associated to it a function that we call the Hamiltonian. And then basically we can, for most functions, or well, possibly not most functions, for a certain set of functions we can define the opposite. So we can take a Hamiltonian and we can produce a Hamiltonian vector field. But unlike in the finite dimensional case, where flat is assumed to be an isomorphism, flat is only injective, so we have no guarantee of existence. But when it does exist, it's unique. Okay, so then, final example. Okay, I'm doing all right for time. Okay, so if we take the Banach space of functions of R, which are twice differentiable and have twice differentiable L2 functions with L2 derivatives. Yeah, cool. And then we take E times E prime, to be, well, I guess the phase space. Then, so this is basically just the example before, but restricted to the W22 case instead of the L2 case. and we have this is d eta. And so here we have this Hamiltonian functional, I guess you could call it. So the point being that this inside the integral is the Hamiltonian for the normal wave equation, but like in the damped harmonic oscillator case, we've added a term kappa z. So if you compare it to this. So with this in mind, so we want to find this vector field xh, and then skipping a bunch of stuff, we find these three equations for, well, not quite for z hat, but for q hat and p hat especially. And then, if we plug them into each other, we get in particular this equation, this ODE for q of t, which then turns out to be the damped wave equation, which I guess I'll just have to take my word for it. But so if you, solutions of this would describe a wave equation, but a wave equation which lost time exponentially, lost energy exponentially rather, with time, such as a plucked guitar string. Okay, and then just to finish off, we can also define co-symplectic manifolds in infinite dimensions, so with co-contact manifolds in infinite dimensions, if those interest you. And yeah, okay, thank you for your time.
Questions?
Yeah?
Probably going to go back to the damped harmonic oscillator example from the beginning.
Damped harmonic oscillator or wave equation?
Damped harmonic oscillator.
Yeah. Yeah.
So the position and momentum equations are familiar, but the one for Z makes you wonder what Z would physically represent.
Yeah, no, that's always a good question. It's a question that I get every time I give a talk like this. I'm never actually quite sure what Z is supposed to represent. I think there are, so in particular, you can do thermodynamics, similar to Adam's talk. You can do thermodynamics with with finite dimensional contact geometry, and then when you do this, Z actually ends up being entropy. So there are cases where it has a very clear physical meaning. Not that entropy really has a clear physical meaning, but you know what I mean. But so, yeah, Z is, I don't know, it's a strange quantity. I sometimes think of it as like, it acts like a sink for energy. It's where the energy goes when it disappears from the system. But even that's not quite true because Z actually does decay over time. So, yeah.
So I've got a partial answer and another question.
Oh, yeah.
You can think of Z as the action, because you can see Z dot is essentially the Lagrangian by the Lagrange transform. So Z, if you integrate Lagrangian over time,
Right.
you get the action. And that's how you get variational principles for contact mechanics as well.
Yeah. That's something I've been meaning to look into actually, so I should have known the answer to that.
And a very speculative question, do you think you could have bi-contact Hamiltonian systems in infinite dimensions? Kind of generalizing the bi-Hamiltonian integral PDEs.
I only actually read about bi contact things for the first time earlier today, because I was looking around an archive. But it's like you've got two contact forms, and their intersection is one-dimensional, something like that.
So in a symplectic case, you would have two symplectic forms with some kind of compatibility condition, and then on that you can build a recursion operator that gives you symmetries.
Yeah, I don't know, but maybe I should look into it. Yeah.
Just this very speculative question. Any other questions? Yes.
When you said that the symplectization procedure is it a junction?
I mean, I was being very vague when I used the word adjoint. Maybe I shouldn't have used the word. It's not like a categorical adjoint or anything, but it's adjoint in the fact that you can sort of get back what you started with.
Is there a way to make it visually?
I don't know. I mean, I guess it might depend slightly on, the category theory of these things tends to get quite ugly quite quickly. Especially if you're keeping within, say, I mean, if you're within Banach spaces, that's quite a nice category, but if you're in Fraser spaces, that's slightly worse. But then there's this category called convenient vector spaces, which is sort of outside of that as well, and that has nice categorical properties. But yeah, I don't know. Maybe I should find out. thing is that to do that, you have to have a notion of infinite dimensional contact geometry, right? Because that's necessarily like an infinite dimensional system. You know, it's like a Hamiltonian system maybe on the space of metrics on a manifold, right? Which is necessarily infinite dimensional. So I'd argue that I don't know. Give me a year and maybe I'll have an answer. No promises though.
You just told me, so what do you mean?
But yeah, I mean, these are like interesting kinds of questions that I think is exactly what this would be useful for. Yeah.
There is also some paper, at least one paper on complex structures and dynamical similarities, where they seem to make the argument that if you don't have an absolute scale, then your expansion would be like the dissipation you see in contact mechanics. I don't know how physically relevant it is. Some people have suggested connections towards cosmology. Right. Final question?
In the beginning, you said your results are in general for a balance space, right?
Yeah.
You don't restrict too much, for example, for a balance space that holds very much.
Sorry, I didn't hear you there.
So in the beginning, you said that your results hold on a general balance space, right?
Yeah. So actually, so basically, because so this theorem, actually, you only care about sort of linear algebra in this theorem. So as long as you're in like a setting where derivatives exist and are nice enough, then actually like all of the smoothness is guaranteed by that. And this condition is actually just a very much an algebraic condition, which I think is interesting. Does that answer your question?
Sorry, yeah. I was going to ask that the example that you gave was around the which is also Hilbert space, right? So I was going to ask if there like an example which holds in a balance space and you use not Hilbert space.
Yeah, good question. I mean, so this example, for example, could be as general as you like. So this could be, you know, any Banach space, however ugly of a Banach space it was. Yeah, I just sort of haven't thought of any nice examples that are physical enough. But yeah, I mean, every Hilbert space is a Banach space, and also obviously Hilbert spaces, because they come with an inner product. So actually, what would happen here is this phi x would just become the pairing between phi and x, which is why I said what I said about this. Maybe would be clearer if I used slightly different notation on this slide. So I'll change that for the future.
Thanks, Fraser, again.